Hi friends, welcome back. My name is Hemant Jadhav, HOD ENTC, ICM Engineering College, Aurangabad. In this video, we will discuss the third chapter of subject ECT, Electronic Circuit Technology, and the chapter name or topic name is Measurement and Signal Conditioning. As I told you, the first chapter of this subject ECT, that means Design of DC Regulated Power Supply, is based on your second year subject EDC. The second chapter of this subject ECT is based on the second year subject HSAD, high speed analog devices, that means op-amp based circuit, which you have already studied theoretically in second year, and here in third year the design of operational amplifier based circuitry that is expected. And this is the third chapter, measurement and signal conditioning. So you should have the basic knowledge of your second year subject electrical machines and instrumentation, that is EMI subject. So this topic is based on your concepts of EMI, electrical machines and instrumentation. So in this chapter we will discuss on different concepts, that is measurement of temperature by using thermistor and by using IC temperature sensors. Then we will discuss the measurement of light intensity or light level by using the photodiode or phototransistor, and then we will discuss measurement of strain by using strain gauge. Okay, so let us start. So before proceeding further, let us discuss about what is an instrumentation system. So this is the block diagram of an instrumentation system. As it can be seen that an instrumentation system is a collection of instruments used to measure, monitor and control a process. So this system can be replaced or can be represented like this also, which consists of medium, sensor, signal conditioning, signal processing and the display. So medium may be a measurand, that means the physical or electrical quantity under measurement is called as measurand or medium. For example, temperature, pressure, flow. If you want to measure these physical or electrical quantities parameters, we have to use sensors and transducers. So the output of sensors are given to the signal conditioners. So signal conditioning is nothing but processing of the signal, as the output of sensors or transducers is very small. It cannot be directly measured or it cannot be directly recorded. So it is amplified, it can be converted from analog to digital signal, it can be filtered out, it can be regulated. So different processes are there: amplification, filtration, regulation, attenuation, etc., etc. Such a block which performs this processing on the signals, it is called as signal conditioner or signal conditioning. And signal processing is one and the same, and that will be given to the display unit so as to display the physical quantity, or it can be, and then it can be measured. Okay, so this is the basic analog instrumentation system. Now let us see the basic digital instrumentation system. All the blocks are same except there is a digital device, microcontroller or microprocessor, as you can see here, which is a digital device. So the physical or electrical quantity which is under measurement, that is sensed by the sensor or transducer, it is processed by this signal conditioning circuitry. As I told you, there may be amplification, attenuation, filtration, analog to digital conversion, because microcontroller and microprocessor cannot work on the analog signal, so there is a need to convert this sensed data into digital format. Okay, so signal conditioning is nothing but converting the data into usable format, and microcontroller or microprocessor is the controlling unit which controls the process, and that data can be recorded, it can be saved in the memory of the microprocessor or microcontroller, and it can be displayed on the display unit. So this is the basic digital instrumentation system. Let us move further. As I told you, the first topic we will discuss in this chapter is measurement of temperature by using sensors, different sensors. So as we know that there are various sensors available in the market for the measurement of temperature, like thermocouple, RTD. RTD stands for resistor temperature detector, thermistor, and semiconductor ICs. Okay, so we know that thermocouple is an active device, active transducer, which is used for measurement of temperature, which works on the Seebeck effect. The effect is invented by a scientist whose name was Thomas Seebeck. It is the effect which states that when two dissimilar metals are joined together to form two junctions, one junction is called as hot junction, another junction is called as cold junction. So when two dissimilar metals are joined together to form a junction, there will be a formation of EMF, and if we measure that temperature difference between the two junctions, it will be proportional to the EMF generated. RTD is the resistance temperature detector, in which the resistance of the transducers or sensor, it depends on the temperature. That means resistance varies according to the temperature. We can see here in this table various features of RTD, like linearity, then excitation, about costing. So out of these four sensors, uh, only these two, that means thermistors and semiconductor IC based temperature measurement, is included in your syllabus. Okay, so thermistor is again the contraction of the term thermal resistor. Okay, you can see the range of thermistor, that is from 0 degree Celsius to 100 degree Celsius. Its linearity is poor linearity. It's require excitation, means external source is required, voltage source maybe, or current source is required, and its biggest advantage is that its sensitivity is very high. Okay, and semiconductor temperature measurement devices means IC based devices having minus 55 degree Celsius to plus 150 degree Celsius range. Linearity and accuracy is 1 degree Celsius. It requires again excitation, that means external source. So we can compare all these four devices here, but we are interested to discuss the measurement of temperature by using thermistor and IC temperature sensors. So as here you can see that before this is the temperature versus resistance graph of RTD versus thermistor. So as I told you, thermistors are thermally sensitive resistors which are used in a variety of applications, including temperature measurement. A thermistor is a type of resistor whose resistance is dependent on the temperature. The resistance varies according to the temperature. The word is a contraction of term thermal resistance. Thermistor differs from the resistance temperature detectors, that means RTDs, in that the material used in thermistor is generally a ceramic or polymer, whereas the material used in RTDs, they use pure metals. Okay, so there are various advantages of thermistors over RTD, like high sensitivity, and we will discuss its advantages. So there are basically two types of thermistors, NTC type and PTC type. NTC stands for negative temperature coefficient and PTC stands for positive temperature coefficient. Means NTC means the thermistors whose resistance decreases with increasing temperature, means as temperature increases resistance reduces. Similarly, PTC means positive temperature coefficient. So the thermistors whose resistance increases with increase in temperature. So resistance increases when temperature increases. These are called as PTC type of thermistors. NTC thermistors are much more commonly used. They are popularly used than PTC type thermistors. So especially for the temperature measurement applications, NTC type thermistors are used. So you can see the different difference between thermistor, graph of thermistor and RTD. Here the temperature is on x-axis and resistance on y-axis. This is the graph for thermistor. As the temperature is increasing in this right direction, the resistance is decreasing, okay, for the thermistor. Similarly, you can see the graph for RTD. As the resistance is increasing, as the temperature is increasing, the resistance for RTD is also increasing. PT100 is a type of RTD. Okay, so this is the difference between resistance temperature curve of thermistor and RTD. Okay, now how is the working principle of thermistor? Let us see. So because the thermistor is a resistive device, we have to pass a current through the thermistor to produce a voltage, and that can be sensed by the data acquisition system, right? So there are two possible ways. So basically you can see a thermistor is connected here, heating element is there. As we increase this applied heat by using the heating element, that means a heater, the as I told you that if the heat increases in PTC type of thermistor, if temperature will increase, the resistance of thermistor will also increase. As the resistance will increase, here we have connected one voltage source, external voltage source. So if there is a change in the resistance of thermistor, the current flowing through the circuit will also change, and the change in current, which is dependent on the change in resistance of thermistor, and the change in resistance will be dependent on the change in temperature, and that change in current will be detected by a current meter connected in series. So this is a simple working principle. We are changing the temperature here, changing the temperature. That change in temperature will cause the change in resistance of thermistor. This change in resistance will cause the resistance may increase or may decrease depending on the type of thermistor. If it is PTC type thermistor, then as temperature will increase, resistance will increase. Then if it is a NTC type of thermistor, then as temperature will increase, resistance will decrease. So this change in resistance will change the current flowing through this circuit, and that change in current will be detected or will be recorded by this ammeter, microammeter, which is calibrated in terms of temperature. Okay, so current meter will show the current reading, but that will be calibrated in terms of temperature. So there are two ways to apply the excitation source. We can apply current source, we can apply voltage source. Here in the first diagram, the current source is applied, thermistor is connected like this. So as we apply the voltage source, so by using this equation, VO is equal to I into R, V is equal to I into R, basic Ohm's law. So we can measure the output voltage across thermistor. So depending on that, we can measure a constant current, we can measurement of the temperature with the help of constant current excitation, that is IEX. In the second diagram, we can use a voltage source, so which will form the potential divider network. RO and RT forms the voltage divider. So VO will be equal to, output voltage is equal to RT by RT plus RO into VEX. So we can measure the change in resistance or change in temperature, that means measurement with constant voltage Vx and resistor Ro. So by using two ways, we can measure the change in current, change in voltage, and ultimately change in the temperature. Okay, so in the exam, question can be asked, design a ambient temperature measurement circuit by using thermistor and operational amplifier. Here I have shown the two ways to connect the thermistors. In the first case, the thermistor is connected in the feedback loop of op-amp. Here it is an inverting amplifier. Op-amp is connected in inverting configuration. As reference voltage is applied to the inverting terminal, non-inverting terminal is grounded. So output voltage will be equal to V reference by Rs into RT. Similarly, the thermal resistor, that means thermistor, can be connected at the input side. So this input resistor and thermistor will form the voltage divider, and that voltage divider will generate a reference voltage that will be applied to the operational amplifier. Op-amp is connected in buffer mode, that is unity gain amplifier mode, and this output voltage can be given to ADC, analog to digital converter, and then it can be applied to the microcontroller or microprocessor, or here directly you can connect the display unit. Okay, so as the temperature changes, the change in temperature will change the resistance of these thermistors. That's why it is shown as a symbol is shown like a variable resistor. So this resistance of thermistor depends on the temperature. As temperature changes, resistance will change. As this resistance will change, as we can see here, the output voltage depends on the value of resistor RT. So as this RT changes, the output voltage will change. That's why you can detect the change. That output voltage can be measured by using a multimeter or voltmeter, and that voltmeter can be calibrated in terms of temperature. So directly it will display the temperature. Similarly here also, the reference voltage present at this point, which is applied to the non-inverting terminal of op amp, that will depend on the values of two resistors which are connected here. As temperature changes, resistance of thermistor will change, the reference voltage will change, therefore output will again change. Okay, so this is the measurement of temperature by using thermistor. Now let us see the advantages and disadvantages of thermistor. As compared to other temperature measuring devices, thermistor is a low cost, its sensitivity is very high, small in size, good stability, high output signal, and there are some disadvantages also. Non-linear output is seen and not suitable for high temperature measurement, and it requires an external power supply to work. Okay, so this is a passive device, therefore it requires an external power supply to work. Okay, another type of sensors which are included in your syllabus, IC temperature sensors, integrated circuits. So this table is though it is not clear here, but the notes which I have provided to you, you can see, you can refer in that. The first device is AD592. I will show once again. This is AD592 device, is a temperature sensor. Then you know the LM35 series, that is LM34, LM35, etc. are these temperature sensors. Here you can see LM34, LM35, LM135, which are very popularly used IC temperature sensors. So we will focus on LM35 and AD590. These two, we will take examples of these two. So you can see the you can refer the manufacturer, the temperature range, etc. So just focus on these two and keep in mind the specification of these two devices, LM35, which is made by Texas Instruments, and AD592 analog devices. So keep in mind the specifications of these two temperature sensors, which can be asked in the exam. So let us focus on LM35, is a 3-terminal IC temperature sensors, pin number 1, to which we have to apply a power supply VCC from 4 volt to 20 volt. This is pin number 1. Pin number 2 is the output pin. Pin number 3 should be connected to the ground. So there are various important features of LM35. Its operating temperature is from -55 degrees Celsius to 150 degrees Celsius. It draws only 60 microampere from its power supply, very low current, and it has very low self-heating, less than 0.1 degrees Celsius in still air. LM35, its operating voltage is from 4 to 30 volt. Then output of IC is varying 10 millivolt per degree centigrade. Okay. Also you can see the features of AD590. You have to keep in mind these features and pin configurations. It can be asked in the exam. So this is the theoretical chapter in which the specification of different sensors can be asked in the exam. So you can see AD590, which is available in 3 packages. Number 1, lead CQFP package, 2 lead package. Then this is 8 lead, you can see it is a DIP like package, SOIC package. NC stands for not connected. So out of these 8 pins, these 4 pins are not connected, and this one is also. So only here you can see plus VCC is applied to 2, minus VCC is applied to 3. Here you can see the 3 pin TO52 is the name of IC package for IC-AD590. Okay, it is available in 3 forms. So what are the features of AD590? It is linear current output is 1 microampere per degree Kelvin, wide temperature range, that is 55 degrees Celsius to 150 degrees Celsius, and different features you can see here from this table. Okay, now let us see how to measure the temperature by using LM35. So LM35 is a temperature measurement sensors which is connected here at the input side. As we know that there are three terminals connected. One is connected to ground, output and VCC. So output terminal is given to pin number 3 of op-amp. That means op-amp is connected is in non-inverting mode and comparator mode also. So here you can see the reference voltage generated by two resistors, 10 kilo ohm and 2 kilo ohm resistor. This reference voltage is applied at pin number 2 and that will be compared with the output of sensors which is connected at pin number 3. So op-amp is used as a comparator here, which will compare the input signals between the applied between the two terminals pin number 2 and 3, and based on these input signals it will generate the output. Okay, so output may be it is equal to plus Vs, minus Vs or 0. Okay, so as you can see here, the output of LM35 increases in proportion to the temperature by 10 millivolt per degree, as I told you before. So if the output of IC is 10 millivolt per degree centigrade is the output of IC, for example, and if the output of sensor is suppose 280 millivolt, okay, so then what will be the temperature in degree Celsius? Okay, it will be, yes, what it will be, it will be 28 degree Celsius, right? So that means the output of LM35 increases in the proportion to the temperature by 10 millivolt per degree. For 1 degree Celsius, the output will be increased by 10 millivolt. So for if the output of sensor is 280 millivolt, then what will be the temperature? So it will be 28 degrees Celsius. So as I told you, op-amp is connected in comparator mode. There will be three options of outputs. So VO will be equal to 0, Vs minus or Vs plus, where Vs is nothing but supply voltage. That means plus Vsat and minus Vsat. So if we consider first case, if V1 is greater than V2, let V1 is the voltage present at non-inverting terminal and V2, V1 is voltage at this point, suppose at non-inverting, and V2 is the voltage at inverting input terminal. So if V1 is greater than V2, that means voltage at non-inverting terminal is greater than inverting terminal, so output will be Vs plus, that is at positive saturation. Similarly, second case, if V1 is less than V2, the output will be minus Vsat, that means Vs minus, and if both the inputs are equal, V1 is equal to V2, output will be equal to 0. So here, for our understanding purpose, this circuit can be used to activate or deactivate device at a particular margin temperature. So it will act like a temperature controller. So for that purpose we have just connected two LEDs for indication of both low green and high red temperature. For high temperature red LED and for low temperature green LED. Okay, so for the first case, if the output VO is equal to Vs, that means plus Vsat, so red LED will be on. For the first case, if output is Vs, here output will be Vs, so anode will be connected to power supply, that is plus Vsat, that is positive supply, and this LED will be on, indicating that temperature is high. Similarly, for the second case, output will be Vs minus, so this Vs minus will be available here, and this green LED will be connected to the negative supply, and this will be on, indicating that output is temperature is low. Okay, and in the third case, V1 is equal to V2, output will be 0, so both the LEDs will be in off condition in this case. So this circuit can work as a temperature controller. Next we can see the AD590 op-amp based temperature measurement circuit. Very simple circuit. AD590 is connected here, and in series with that a 10 kilo ohm potentiometer is connected. Current flowing through the AD590 is equal to 1 microampere per degree Kelvin, and across this resistance of 10 kilo ohm, a voltmeter is connected which varies whose voltage varies 10 millivolt per degree Kelvin. Okay, So AD590 and 10 kilo ohm resistance, these two forms a voltage divider circuit. As temperature changes or it varies, the resistance of this IC AD590, it varies accordingly, and as it forms the voltage divider, so temperature change will cause the resistance change, and this resistance will cause the output voltage change. And this voltmeter can be calibrated in terms of temperature so that we can measure the temperature. So it causes a change in current through the sensors at a rate of 1 microampere per degree Kelvin. Okay. Now, what are the advantages of IC temperature sensors over other thermistor, thermocouple, or RTD sensors? So, it is easy to install on your PCB as it is a package. So, it will be with the processing circuitry, that means a transducer, sensing plus conversion into usable format, and it is a package, so easily can be installed on the PCB. User friendly output format include non-chip signal conditioning circuitry. On chip signal conditioning is there, as I told you. So what are the disadvantages? The temperature range is low, that is minus 55 to 200 degrees Celsius only, and the response time is important. In RTDs or thermistors, they respond in 1 to 10 seconds, whereas IC temperature sensor respond in approximately 4 to 60 seconds. So response time is quite greater as compared to other sensors, and responsiveness to temperature changes depends on package size. Smaller packages responds more quickly. These are the disadvantages. So we can also add a thermometer to your digital multimeter by referring this circuit diagram. If the facility of temperature measurement is not provided in your multimeter, you can use IC LM35, and you can modify your multimeter for the measurement of temperature by using this circuit diagram. Very simple. Battery connection, batteries are already there in your multimeter. You just have to add the LM35 temperature measurement sensors and make the circuit diagram like this. You will get the ambient temperature on the display. Okay. Now measurement of light by photodiode. Okay, light intensity or light level measurement by using photodiode. Here you can see the symbol of photodiode, PN junction diode with light rays symbol, and this is the basic working principle of photodiode. Okay, so as you can see, the light rays, that means photons, are uh, getting on the photodiode, and we know the working principle of photodiode. That means a photodiode is a semiconductor device which converts light into current. The current is generated when photons are absorbed in the photodiode. Photodiodes can be classified by its functions and construction in different types like PN photodiode, pin photodiode, Shockley type photodiode, APD, that means avalanche photodiode, and etc. So this in this diagram, in the first diagram, the basic working principle of photodiode you can understand from this diagram. A photodiode is a special diode whose resistance varies with light, and no current, ideally no current flows through the photodiode when it is in complete darkness. Okay, practically very small and negligible current flows through the photodiode, even if it in dark condition, but that is very small and negligible. So we can say that a photodiode is a special diode whose resistance varies with the light intensity. Okay, so here we have connected one battery and a current measurement device. As the light intensity will increase, or it will change, there will be change in the resistance of photodiode, and the current flowing through this circuit will change. So light intensity falling on the diode will change its resistance, and this will change the current flowing through this circuit, and that will be recorded in the current meter. So very simple working principle. Change in light intensity will change the resistance, and that change in resistance will change the current flowing through the circuit, and that current meter will be calibrated in terms of temperature so that it will indicate the temperature. Okay, so here in this graph you can see various curves for the currents in the third quadrant of this system, coordinate system. So when observing the current voltage characteristics of photodiode, we can notice the different waveforms in different quadrants of coordinate system. In the third quarter, characteristic shows the uses of photodiode as a photodetector, that means light sensors. You can see the different curves for current I1, I2, I3 and I4. So here it works in reverse bias, therefore it is mentioned in the third quadrant, and current in microampere, that is also negative value. So I4 is greater than I3, is greater than I2 and is greater than I1. So at low intensity there is a low current I1. As current intensity increases, the current increases. Okay, so photodiode is special diode whose resistance varies according to light, and practically, ideally, there is no current flow through the diode when it is in complete darkness. There is an example of photodiode BPW34 is a number of photodiode which is available in the market. We can see the advantages and disadvantages of photodiode. So photodiode is having excellent linearity with respect to incident light. As light changes, resistance changes quickly, so response is very good. That is called as linearity. It has low noise, wide spectral response, mechanically very rugged and compact, lightweight and long life. There are certain disadvantages also. No amplification of the control current takes place. There is only sensing, and amplification is not done here. As a result, the amount of current that can be used in the given circuit is limited by the amount of current the device can handle. So as there is no amplification, very small output, so which can be overcome by using another device, and that another device is a phototransistor. We will discuss it later on. So this is the light intensity measurement using photodiode. Here you can see the concept. The photodiode number is BPW34, which is a high speed and high sensitive silicon pin photodiode, and available in the flat plastic package. The photodiode can be used either in zero bias or reverse bias. It works in reverse bias or zero bias. So diodes have extremely high resistance when reverse biased. This resistance is reduced when light of appropriate frequency, it will be incident on the junction. Hence reverse bias diode can be used as a light detector by monitoring the current flowing through it. Coupled to a 10 kilo ohm resistor, and given the specifications of BPW34, a simple relationship between the lux and the voltage is can be here it can be seen in this diagram. Here you can see two circuits. In the first one there is switch high, and in the second case it is switch low. So here the photodiode is connected in reverse bias mode, here also in reverse bias mode, and the photodiode and this resistor connected in series will form the voltage divider network. The output voltage can be calculated based on the voltage divider formula which we have studied before. So it can be connected to get switch to high output as well as switch to low output as per these two circuit diagrams. Just a potential divider. Change in light intensity will be detected by the BPW, that means photodiode, which will change the resistance of this photodiode, and that change in resistance will change the output voltage, and voltmeter connected at the output side will be calibrated in terms of temperature, in terms of light intensity. Okay, now another circuit by using by using operational amplifier. So here photodiode is connected, and in series with that a resistor in parallel, the resistor is there. So change change in light intensity will change the resistance of the photodiode, which will change the current flowing through this terminal. So this will be acting as a current source. This photodiode is acting as a current source, and whenever there is a current source, the resistor is connected in parallel. This op amp is connected to I to V converter format. In configuration is I to V converter, as the input current is applied to the non-inverting terminal. So this is a non-inverting I to V converter, current to voltage converter. The output voltage will be measured by the voltmeter, which can be calibrated in terms of light intensity. So by using op amp, again we can measure the light intensity directly. Light intensity falling on the diode will change, its resistance will change. As the resistance will change, there will be change in the current which is applied to the non-inverting terminal of op amp, and therefore the voltage will change, which will be measured by the voltmeter and which can be calibrated in terms of light intensity. So as I told you, there are certain disadvantages of light intensity measurement by using photodiode. There is no amplification. So the next device is a phototransistor, which is a combined package of photodiode along with the phototransistor. That means sensing plus amplification. So working principle of phototransistor is same as photodiode. This is a combination of photodiode with a transistor. So light intensity will be light rays or photons will be sensed by the photodiode or phototransistor, and the resistance of phototransistor varies according to the intensity of light, which will change the current flowing through this circuit. As a voltage source here it is applied, so current flowing through this circuit will change. That will be detected by this meter, which can be calibrated in terms of light intensity. So this is the basic working principle. Here is the symbol of phototransistor. Both are the symbols of phototransistor. The popular numbers which are available in the market: FPT100A and MRD3050. Here you can see the characteristics of phototransistor like an ordinary transistor. VCC versus IC, VC versus IC, output voltage versus IC. There is a dark current, that means when light intensity is 0, the current flowing through the transistor is almost 0. Practically very small current flows through the device in the dark condition. As light intensity increases, the current flowing through the device will also increase. Okay, so there are some specifications of FPT100. You have to remember these specifications. This is the pin configuration: pin number 1, 2 and 3, pin number 1 ground, 2 VCC and 3 output voltage. These are the specifications of phototransistor. So if we compare photodiode with the phototransistor, the dark resistance of photodiode is of the order of 2 mega ohm, and here it is of 150 kilo ohm. And at room temperature with the 60 watt lamp, the photodiode resistance is 200 kilo ohm, and that of phototransistor is 5 kilo ohm. Okay, now let us move to the measurement of strain by using strain gauge. Okay, so before proceeding further, what is strain and stress? We will discuss on that. In many industrial application, it is required to measure the different physical quantities like strain, force, pressure, flow, etc. The most popular electrical elements used in force measurement, that includes the resistance strain gauge, the semiconductor strain gauge, and piezoelectric transducers, etc. Different measurement principles are based on strain gauges are strain gauge, piezoelectric transducers. For the force measurement, we can use load cell. For the pressure measurement, diaphragm to force to strain gauge. Then for flow measurement, differential pressure techniques, etc. So what is what is a stress and strain? Basically, a strain is relative to change in shape or size of an object due to externally applied forces, and stress is the internal force per unit area which is associated with the strain. So based on that, there is a Hooke's law: stress is directly proportional to strain. So when any external force is applied to the object that is made of elastic material, They produce changes in the shapes and size of this object. This change in shape can be expressed in terms of strain and stress. Okay, so here Young's modulus is given by that Hooke's law. Stress by strain is equal to stress by strain. So what is a stress and what is strain? Stress can be defined as force per unit area of a material. Stress is equal to F by A. F is force and A is area, and sigma is stress. Okay, force per unit area. Similarly, what is strain? Strain is nothing but the extension per unit length, change in the length. Okay, here you can see it can be denoted as epsilon, which is equal to L minus L0 divided by L0, where L0 is the original length, delta L is the change in length by original length L0. So strain is equal to L change by L, change in the length. Elongation or compression per unit change is called as strain. Okay, the strain gauge is an example of passive transducers, which uses the electrical resistance variations in the wire to sense the strain produced by a force on the wires. Okay, so it is a passive transducer. Strain gauge is a passive transducers whose resistance changes depending on the applied force. Okay, so it is a very versatile detector and a transducer for measurement of strain, weight, pressure, mechanical force or displacement. In this compressive stress tends to compress the wire and thereby decreases its length and increases its cross-sectional area. And exactly opposite of this, a tensile stress, which tends to elongate the wire, and here it will increase the length and decrease its cross-sectional area. The combined effect of tensile stress is an increase in resistance, and as seen from the equation here. So here you can see a strain gauge is a device whose electrical resistance varies depending on the applied force. Okay, the strain gauges are available in different packages, like you can see here. The first is wire gauge type, then second is foil gauge type, third one is a semiconductor gauge type. Okay, these three packages. Now we will discuss how we will measure the temperature, the strain by using strain gauges. As I told you, there are three types of strain gauges, like wire gauge, which are having different characteristics, different advantages. Like they are reasonably inexpensive. They can pull off very overall accuracy better than plus minus 0.1%. They are available in short gauge length and have small physical size, etc. Foil and thin film type strain gauges are also having its own advantages and disadvantages. So one can refer the advantages and disadvantages of all these three types of strain gauges. Now, how to measure the strain by using strain gauge? This is a Wheatstone bridge, which I have shown here, which can be used for the measurement of strain gauge. Wheatstone bridge is used for measurement of unknown resistance basically, and whose output can be amplified by using the operational amplifier, and then it can be displayed. So here light dependent resistor is connected in the lower diagram. This is not in the syllabus, but I just shown you for the knowledge purpose. Wheatstone bridge is the bridge which is used for the measurement of unknown resistance, and in the balanced conditions, that means when all four arms of this bridge, these four arms of this bridge are having equal resistance, then the output voltage between these points C and D is equal to 0. So in balanced condition, the output is 0, and when the bridge become unbalanced, there will be some output voltage. Here also, this is the Wheatstone bridge whose output is applied to operational amplifier, and then the transistor which is a driver transistor to drive the relay. Okay, so there are three combinations here I have shown. In the first case, a single strain gauge is used in the Wheatstone bridge. So R1, R2 and R3, these are the known resistances, and this is the unknown resistance. Strain gauge is connected in the place of fourth resistor. Here we can connect 4 strain gauges for more accuracy. We can connect we can use the 3 configurations or 4 configurations, 4 strain gauges in the Wheatstone bridge, which are shown here. So a strain gauge is a device whose electrical resistance varies according to the applied force. To measure such small changes in resistance, the strain gauges are always used in a bridge configuration with a voltage excitation source. The general Wheatstone bridge consists of 4 resistive arms with an excitation source, means an external source VEX, which is applied across the bridge. When all 4 arms, resistive arms, are matching, that means equal, with identical values, the output voltage will be 0, and you will get 0 volt. So VO will be the non-zero when there will be unbalanced in the bridge. A bridge will be unbalanced when all the resistive arms, the change in the resistance will be there in the any resistive arm. Okay, so as we know that when the force will be applied to this strain gauge, there will be change in the resistance of strain gauge. That change in resistance will unbalance the bridge, and as soon as the bridge will be unbalanced, the voltage that will be proportional to the voltage present between these 2 points. So more number of strain gauges will increase the accuracy here. That is the concept. In a single strain gauge used, the accuracy will be less. When all 4 arms, 4 strain gauges are used, the accuracy will be more. The output of this Wheatstone bridge can be applied to the operational amplifier here, which will be amplified, and the output voltage can be measured, that will be calibrated in terms of change in the force or stress. Okay, strain. Then you can see this is the measurement of strain by using strain gauge. Here what we have applied, we have connected 4 strain gauges in the Wheatstone bridge configuration, and it will be applied to the instrumentation amplifier. So output of Wheatstone bridge will be detected when the bridge will be unbalanced, and bridge will be unbalanced when there is a application of force. That strain will be detected by this Wheatstone bridge, that will be applied to the instrumentation amplifier, which will amplify the output of Wheatstone bridge, and it will be measured at the output by using a voltmeter, and that will be calibrated in terms of strain. Okay, so by using this we can measure the strain by using strain gauge and operational amplifier and Wheatstone bridge. Okay, if any queries, we can discuss on the groups. So up to this video, that is all about the measurement and signal conditioning. Thank you. We will